Hi, today I'm going to start to review the material we have so far, go through some of the important points of each section we had so far. I'm going to start with the vectors and we'll go ahead from there. The very first thing that we are doing is that in the vector we have either 2D vectors or 3D. In most cases in a statistics throughout the course, if we are dealing with the 2D problems, what we are going to do is that we will find the component of all the forces in the x and y direction and then do all the calculation as a scalar. It means that we just assume the sign, so everything is a positive direction of x is positive, everything is a negative direction of x is negative. The same for the y direction, everything is the positive direction of y is positive, in the negative direction of y is negative. So if you have 2D, just find the component of all forces in the x and y direction and then simply work as a positive negative sign for each force. On the other hand, if we are working in 3D, it's much easier to work with the Cartesian format. In other words, instead of having the component, just write the vector format and then start to work with that. Let's go back to the 2D. One of the things that you probably need to remember is that how to find the component on x and y direction. So I'm going to give you just a couple of simple examples. So assume that's what I have as the x and y, and I have a vector like this, and this is the theta. Remember, always the component that is next to the angle, the component that actually touch the angle, is the cosine. So it's going to be f cosine theta. And the component that does not touch the angle is the sine. Okay, another example, for example, assume this time I'm going to have it here and here, and I have the force, and this is the theta. Or let's make it, this is the theta. The same here. The component that touched the angle, the component that touched the angle is going to be cosine theta. And the component that does not touch the angle is going to be f sine theta. So don't get yourself confused about x and y. Just look at it. The component that touched the angle is always cosine. So here it touched the angle is cosine. Here this one touched the angle is cosine. And the one that doesn't touch the angle is sine. Same here. And if it's not in that format, if assume you have your x and y axis like that, and you have this is the f and this is the theta. The same here, when you want to find the component that touched the angle, so this one touched the angle, so it's going to be f cosine theta, and the one that does not touch the angle is going to be f sine theta, regardless of which one is x, which one is y. This one touched the angle is x, this one doesn't touch the angle, it's going to be y. So if you have a 2D problems, the very first thing you need to do, just find the component in the x and y direction, and then start from there and work in a scalar value. There is a positive, negative. So everything is the positive, x is positive, everything is negative, x negative. The same for the y direction. Everything is positive, positive, everything is negative, y is negative. When we are dealing, when we are starting to work with the 3D problem, there are a couple of things that we need to know. The first of all is the position vector. What was the position vector? So if I have the if I did draw, so 3D, and I have 2 points A and B. I have 2 points in that A and B. The position vector is the vector connect A to B. So the vector goes from A to B. And we usually show it as a RAB. The position vector, how we calculate the position vector is that we say that the position vector is xb minus xai plus yb minus yaj plus zb minus zak. So this is the position vector, is a vector that connects A to B. Another vector that we need for our calculation is the unit vector along AB. And it's the same, the only difference that it is along the line AB, but its length is 1. Its magnitude is 1. So it is along the line AB, but has a magnitude of 1. And the UAB is RAB divided by magnitude of RAB. And the magnitude of RAB is a square root of component to the square. So xb minus xa squared plus yb minus ya squared plus zb minus za squared. So these are the two vector we need. So the position vector and the unit vector. The position vector is the vector goes from point A to point B. The unit vector is the vector along AB but has a unit of 1. Remember that if you are talking about the unit vector along the x direction is I, the unit vector along the y direction is j, and the unit vector along the k direction, along the z direction is just k. The unit vector along the AB is this. So that's how we work with that. Now, if we want to find the force in 3D domain, that's most of the time that's what we need to do, is to find the force in 3D domain. What we will do is that if we have again the x, y, and z, assume that's the x, y, and z. So I have this, and I have a force that is along line AB. It is along a line AB. I want to find that force. That force, the vector of that force is the magnitude of that force times unit vector of AB. So every time we want to find the force, the force as a vector, that's how we are going to do that. So we will go there, we want to find the position vector between A and B. Then from the position vector, we want to find the unit vector from A and B. And then from the unit vector from A and B, we will find the force itself by using this equation. That's how we will find the forces in 3D. And almost in all the 3D problems we are doing, that is the only equation we need. That's the only equation we need. And that these two are the way that we calculate the UB. So that's the basics of how we deal with the vectors in 3D format or in Cartesian method. After that, after we will dealing with the forces, the next part that's probably important for us is equilibrium of particles. So how we are dealing with the equilibrium of particles. So like in that. So equilibrium of particle the equilibrium particle, when we are talking about equilibrium particle, is the situation that all the forces is going through a single point. So we have a single point that all the forces go through that. Again, we may have it in 2D or 3D. If we have it in 2D, so we have, that's a point, and we have F1, F2, and F3. what we are going to do when we have it, the first thing first, find all the components of these forces in the x and y direction. And then after you find that, that's the very first step we do, find all the forces in x, and so it's the f2x, it's the f3x, so it's the f1x, and then all the forces in the y direction. So it's going to be f1y, it's going to be f2y, that's going to be f3y. And after we have all the forces in the x and y direction, simply write sigma f x is 0 and sigma f y is 0. For example, here if I write the sigma f x is 0, f1x is positive because it's in the positive direction of x, minus f2x because it's in the negative direction of x, minus f3x because this one's also in the negative, is 0. The same for the fy. I have f3y, let's go from 1 to 3. So I have f1y, which is negative because it's looking downward. Then I have f2y is going downward. That one is also be negative. And I have f3 is going upwards, is positive. So it's going to be f3y is 0. And then you can start to work with it. So every time that we have a 2D problems, the very first thing you do, find the components in the x and y direction, and then try to add them in each axis together and work from there. But if you have it in the 3D dimension, if you have the here's the 2D format. If you have them in the 3D format, instead of using as a scalar format as what we did, try to write it as a Cartesian. So assume I have x, y, and z, and then I have a point somewhere here, and I have this time I have 3 forces going there. For example, assume this point is D. Just assume this point is D. So I have and this is, for example, is the FAD. I have, for example, FBD, and I have FCD. So it says the BD. So I have 3 forces that go into point D. The only thing, the first thing I have to do is that I have to go and find the position of, it's the AD, BD, CD. So go ahead and find the position of A, position of B, position of C, and position of D. So find the position for each of the points you have. So it's assume this is the A here, this is the point A, this is the point B, and this is the point C. So I assume these are the 3 forces I have. So these 3 forces go through point. So find the position of A, B, C, and D. Find the position of those points. Then find the unit vector and the position vector and unit vector for all the forces. So go ahead, say find the RAD, and then find from there. After you find RAD, find the UAD, and then when you find the UAD, you will find the FAD as a FAD as a FAD times UAD. The same here, go ahead for the second one, find RBD, then find UBD, same as what we did there, and then find the FBD as a FBD times u, b, d. And then for the last forces, so go ahead, find the r, c, d, then find u, c, d, and then find f, c, d, f, c, d, u, c, d. After you have these three, after you find all the forces, the next step that you need to do is that just simply go ahead and add all the forces together, sigma as a vector, 0. So when you put that, when you get the sigma f is 0, what you're going to get is you're going to get FAD plus FBD plus FCD is 0. When you have that, after you write that, go ahead and then write all the I component together, then write all the J component together, and then write all the K component together equal to 0. So you write it like that, then just simply add them together. After you add them together, just simply go and put all the I component, all the J component, all the K component together. And by the time you get there, for this to be 0, this should be 0. This should be also 0. So this should be 0. In other words, this first one is sigma fx is 0. This one is sigma fy is 0. And this one is sigma fz is 0. So one more time, what we will do is that if you have the 3D forces, you have to find each forces as a vector. To do that, go and find points that are on the line of action of each forces. So for example, is the force AD, I will find the position of A and D. For FBD, I will position of B and D. So find the position. And after you find the position, find the position vector for each of them. For example, for AD, I will find the position vector. And then as this. And then after I find the position vector, I will find the unit vector. And after I find the unit vector, I use this equation to get the FAD as a vector. So it's gonna give it's gonna have I, J, and K component. The same here, FBD gonna have I, J, K component. The FCD is gonna have I, J, K component. Then simply add them together, and then put all the I component together, put all the J component together, put all K component together, and to be 0, all the I component should be 0, all the J component should be 0, all the K component should be 0, and that's I will say that majority of the working in 3D, that's all the steps you need to go through. So to get that, the one I will show it one more time here. Assume that's the AB, and there is a force here going. I will put it here, for example. This is a force AB. So if you want to find the force FB, you find the position vector from A to B. So the very first, before that, you find the position of A, you find the position of B, find the position vector AB, then find the unit vector AB as this, and then the force AB is going to be magnitude of AB times unit vector of AB, which eventually it will comes out something like that. So it's going to, after you simplify it, you will get something like that. If AB in the x direction I plus F AB in the y direction J plus F AB in the z direction K. So when you simplify it, eventually you get something like that. And so that's how we will do the equilibrium particle in 3D. Almost all the problem in equilibrium particle in 3D would be solved in this method. The next part that we need to talk about it is the moment. So we know how the moment works. Similar to what we have for the forces, that's in 2D and 3D. Also, we will have the moment in 2D and 3D as well. I'm gonna show you how to work with the moment in 2D and 3D format. So, moment in 2D and 3D. First, we will start to work with the 2D. The very in the basics of that, if I have a point O, I have a force F. The moment of force F about point O is the F times D, is the force magnitude times the normal distance between force and point. So in other words, I will draw a line from the point with a normal angle to the force. So that's going to be D. That's how we do it in, so that's the moment. That's how we will work on that. Generally, when we are working with 2D, we will consider a rotation direction as a positive. Usually, we'll consider the counterclockwise as a positive. So here, for example, if you look at that, this one is going to rotate it. This one is going to rotate it clockwise. So it's going to be negative. To make sure that everyone understands, so I will put the sign here. I will say that, okay, that counterclockwise is positive. So this one is negative because it's rotating clockwise. This is just we assume that the counterclockwise is positive. You can use the other way and consider clockwise positive. So here we consider counterclockwise positive, and this one rotated clockwise. Each time that you want to see if it is going clockwise or counterclockwise, one of the easiest ways is that assume there is a cord or rope connected from the point to the force. That end of the cord on the point does not move. The other end of the cord can move. So if you push it with this, you pull it with this F, which direction the rope goes? In this case, the only way the rope can go is go to the right, or other way, it only can rotate clockwise. Now, when we have the 2D and we want to do, this is a very basic, not the more general format. So assume I have a point O here, and then I have a force like that. Let's see, I have a force like that, and I want to find that moment of F about O. When we are dealing with the 2D problem, the very first thing we will do, and we will say that find the component of forces in the X and Y direction if they are not. So that's the very first thing we will do. So it's going to be Fx and it's going to be Fy. So that's the very first step that we will do. Fx and Fy we will find. Draw the line here. So in the 2D, always find the component in the X and Y direction. Now I want to find the moment about the O. So I'm going to say sigma m about point O. And then I have to decide which direction I want to be positive. So I consider counterclockwise to be positive. I start with the Fx. To find the Fx, so I know that's the force time distance. So the force is Fx, I know that. Then I need to find the distance or also the rotation direction. So to find the distance, when you want to find the distance, always extend the line of action and then draw the normal line from the point to the line of action. And I would call it D1. So this is the normal distance, so Fx, so it's going to be Fx D1. Now I want to see, is it going clockwise or counterclockwise? I assume there's a rope connected from here to Fx, only Fx. And the Fx pull that rope here, so it's going to rotate it clockwise. so it's going to be negative. Then I will go to the fy, so I know the fy. Then I need to find the distance, the normal distance between the fy and from the point O. So extend the line of action. There are the normal line from the point to the line of action. I will call it D2 here. So Fy times D2. And this time, if I consider a rope connected from O to Fy, the Fy is going to bring the rope this way. So it's going to rotate it counterclockwise. So it's going to be positive. So this is how we are working with the, if the moment is in the 2D, this is how we deal with that. If the moment is going to be in 3D, then we will go on working in the Cartesian method for that purpose. So assume here that I have, again, X, Y, and Z, and I have point A, and I have point B. I have a force at point B. I want to find the moment of F about point A. The moment of F about point A is going to be the position vector from A to B, cross product of F. So it's going to be position vector from A to B. So that's going to be RAB, cross product of F. And we know that the magnitude of this is MA, or in other words, the cross product of RAB. Cross product of F is determined by determinant I, J, K, RAB in the X, RAB, Y component, RAB, Z component, and then Fx, Fy, and Fz component. So we can calculate this determinant and to find that vector. So it's going to give us the moment of F about any point. So when we want to find the moment of force, we'll do that. And also, if we don't know the F, again, the F here is the magnitude of F times the unit vector of F. So whatever is the unit vector along the F. So this is going to be the as we did it in 3D. So it's a unit vector along the F. Whatever, if we have, for example, assume there's another point C here. So let's make it another point C here. So that unit vector is going to be unit vector of BC. So F is going to work with the unit vector of BC. So that's how we will do the moment in 3D format if we want to calculate a moment in 3D. Similarly, if you have, let me see here. If you want to find the moment about an axis, if we can find the normal distance is like the previous FT, but if we cannot, again, it's a very similar thing. So I'm going to draw that. So it's going to be X, Y, and Z, and I have point A, point B, point C, and I have a force at point B. I want to find the moment of that force about an axis going through here. Assume that's the axis AA. I want to find the moment of that F about AA. It's very similar to what we had here again. So this time the moment about that axis, the moment of F about that axis is the unit vector about that axis. The unit vector about that, it's going to be dot product, and it's going to be R cross product F. And the R here, for example, here is R is going to RAB. So again, it's going to be, if this is the same thing here, so it's the RAB. Yeah. So that's how we will find the F the same as here. The F is going to be F times UBC. So that's the F. It's going to be UBC. And the U is the unit vector about axis A. So it's going to be about X. So unit vector in. That's the unit vector A. So it's the unit vector in axis. Remember, I draw the R from A to B, but it can go from anywhere on the A to anywhere on the line of action. Similar here, the RAB can go from anywhere from A to anywhere. It can go from A to anywhere on the line of action there. And this magnitude, if you want to calculate that, this UA would be the determinant of UA in the X, UA in the Y, UA in the Z, and then RAB in the X, RAB in the Y, RAB in the Z direction, and then FX, FY, and FZ. And we can use this determinant to find that. So these are the two. There one thing I should mention is that if you have a force in the X or Y or Z direction, make sure that we are not going through all these things. If the force is in the X direction, so it's the magnitude of the force times I. It's the force in the Y direction, it's the magnitude of the force in the Y, and the force in the Z direction is the magnitude force in the Z times K. So this is this example here. So one more time, that's how we do that. If we have again a point, the point here, and let's have X, Y, Z. If I have forces that are going to be in either of X, Y, and Z direction, if I have, for example, F1 is going to be exactly in the X direction, then F1 is going to be the magnitude of F1 just I, because it's just in the X direction. If I have a F2 that is in the Y direction, the vector of F2 is going to be just simply F2 times J, the magnitude of F2. And if I have the F3 is in the Z direction, the F3 is going to be magnitude of F3 times K. So remember, if your force or vector is in the I, J, and K direction, you don't need to use this equation. Just simply put I, J, K. If it is not in the X, Y, Z direction, and assume I have the F4 that is not in any of them, then F4 I have to go is the magnitude of F4 times the unit vector about the unit vector along F4. So only use this equation if it's not along X, Y, or Z. If it's along X, Y, or Z direction, so just use it I, J, K, and it's much easier to do that. The next topic I will very quickly go through that is the distributed load. What if we have a distributed load, and how we handle the distributed load? In most cases that we're dealing with the distributed load, we have either the shape of the load is either trapezoid, is either rectangle or triangle. So distributed load. So I will just go through those two simple ones. When we have the distributed load, what we want to do is that we want to replace the distributed load with a single force or a couple of single loads. So we want to get rid of that distributed load. If we have example here, if I have a distributed load, assume is 10 meter, and this one is, for example, assume is 100 Newton per meter, and I want to say that this one is equal to, I want to replace distributed load with a single load. So the value of the load is always the area of the load. The value of the single force is the area underneath of the load. So I would know that the magnitude of that, the magnitude of the force I have, is the area after that. So the area is I have a triangle with the width of 10 and height of 100. So it's going to be 10 times 100. So it's the area of that rectangle. And where that force is applied, it will be applied on the centroid of the load. So I have the rectangle. So the centroid of the load is going to be right at the center of that rectangle. So it's going to be, I have a force right at the center. So if this is a 10, this is going to be 5. It's right at the center. And the magnitude is just 1000. So the magnitude is the area underneath of the force, and the location is going to be applied is on the center. Another simple shape that we may see in when we're working with the distributed load is the triangle. Let's see how we work with triangle. If we have a same, assume that we have it, but this time we have a triangle instead of the rectangle. So it's that we have. So it's going to be, assume it's a 50 Newton per meter, and it's again is a 10 meter, the length. So what we want to do again, we want to replace that with a single load. So we'll come here, we draw that. So the magnitude of the force is area underneath of that triangle. The area of that triangle is half of its height times its base. So it's going to be 250 Newton. So that's the magnitude. Just the area of that triangle is the magnitude. Where it's going to be is going to be at the centroid of the triangle. The centroid of triangle is here. We know that the centroid of the triangle is 1/3 from the base and the 2/3 from the other end. So it's 1/3 and 2/3. So I know that's going to be here. The magnitude is 250, and the distance here from this end is 1/3 of 10, and from that end is 2/3 of 10. So that's the magnitude. So we will replace the distributed load with a single load. If we have the shape that might not be as simple as that, most of the time we can simplify that shape into the simple shape. So how we do that, for example, let's assume again we have the 10. But this time, assume we have a load like the trapezoid load. So we have 100. So assume this is what we have. So it's 100 Newton per meter here. And it is 150 Newton per meter. To work with that, I will go ahead and break down that trapezoid into two parts. I will say that it's going to be two parts. There's the one rectangle down here and one triangle on the top. And then I will add them together. So I'm going to say that, okay, this one is equal. And I draw that. So first I will do for the rectangle. If I look at the rectangle, the magnitude is 100 times 10, the magnitude of this rectangle here. And where it's going to be at the center. So I have replaced this part of the load, the rectangle part of the load, with 10 times 100. And when it's going to be right at the center. Then I have the top part, the triangle part. So I will calculate the area of that triangle. And where it's going to be at the centroid of that triangle. So it's this one. And the other one is going to be right here at the centroid of that triangle. So it's going to be somewhere here. And then the magnitude is area of that triangle. So the length is 10. Half of the 10 times. And this is 50. So if this is going to be 100, this is going to be 50. If the total is 150, so this part is 100, this one is 50. So it's going to 10 times 50. So it's 10 times 100, the half of that is 50. And where it's going to be located is 1/3 of 10. And then we will start to work with that. So anytime that we have the distributed load, just go ahead and replace the distributed load with one or series of single forces, and then start to work with those forces. The next part that I want to talk about is how to do the problem in that case is the equilibrium of the rigid body. What if we have the equilibrium of the rigid body? So these are the steps that again we have for the equilibrium rigid body. We may have it in 2D or 3D. First I will look at it if we have in 2D. If you have in 2D, this is how we are going to handle the case. The first of all, what we are going to do, the very first step, find all the forces in the x and y direction. So find all x and y component of forces. So find all the x and y components of forces. That's the very first step. That in 2D. That's what the first thing you are going to do. Second steps is we will go to do the free body diagram. And to do that, the very first thing you will do that just disconnect the rigid body from anything. Remove everything from the rigid body. Disconnect it from anything is connected to just the body itself. The next step, put all external forces and moment, all external forces and moment on body. So draw the rigid body and then add all the external forces and the moment to that. After we do that, the next step, let's say not replace, just add reactions for all support. So we remove the support. We want to make sure the object stay in a place. So after we add the external forces which tend to move the object, we are going to add the reaction from the supports which try to prevent object from moving. After we have all that, the last step is just go ahead, write the equilibrium equation. Sigma fx is 0, sigma fy is 0, and sigma m about any given point is 0. That's by the time you are writing these equations, you will get all the unknown you had. Almost on all the 2D problems that you have the rigid body equilibrium, that's the steps that we'll go through, and I will show you with a quick example. So assume I have this object here, and I have A and B, and there's a force F1, or let's make it number, so you know it's known. So assume it's 100 Newton. So the very first step I'm going to do that I will find the x and y component for that. So it's going to be, if this is a theta, assume, so it's going to be 100 cosine theta and 100 sine theta, and we know the theta will be given in the problem. So find all the x and y component of forces we have. If you have more forces, find all the x and y component. Then free body diagram, just draw the beam here, the body here, nothing on there, remove all the support, remove all the force. Then add all the external forces and all the external moments on the body. Here we don't have external moment, but we have external forces. So I'm going to put that 2 forces here. So it's going to be 100 sine theta, it's going to be 100 cosine theta. After that, I will replace each support with its reaction. For example, at point A, I know that I have a pin, and the pin prevents it from moving up and down, prevents it from going left and right. So I have 2 reaction there. So one reaction to make sure it's not going up and down, and one reaction to make sure it's not going left or right. The B is the roller. It only prevents it from going up and down, so I only need one force, one reaction at B to make sure it's not going up and down. After we I get to this point, I just write these 3 equations in an order that works the best for me. It's always, remember, you may first need to use M or use Fy, or if it depends on your problem. You can switch those the order of those equations. So use these 3 equations to find the unknown. For example, here the unknown is Ax, Ay, and By, so we can find them. Almost in all the 2D problems that we have, we work with the 2D equilibrium. That is how we are going to solve the problem. Working with the 3D is less or more just similar to the 2D one. Again, we'll go through the almost the similar steps for that case. Again, assume this time if we have the 3D, I'm gonna, if you have the 3D, this time the very first step, almost the very first step we need to do is find position vector and unit vector, and then write each force as vector using this equation. So F is the magnitude of the force, the unit vector. So for each force, the very first step we will do, go ahead, find the position vector, find the unit vector, and then find the force for that specific forces. That's what we need to do, and then do the free body diagram. So do the free body diagram. Remove all the forces, all the connection, everything from the diagram, just the free body diagram. Then put all external forces and moment on body. So go back and put all the moment and forces, all the external moment and forces you have on the body. Then add reactions for all supports, and by the time you get there, you write equilibrium equation in the vector format, which is going to be sigma f is 0, and then sigma m about any given point is 0. And by solving those two equations, these equations eventually going to give you two sets of equation, which is going to be sigma f x is 0, sigma f y is 0, sigma f z is 0, and the same here is going to give you sigma m x is 0, sigma m about y-axis is 0, and sigma m about z-axis is 0. So these two eventually lead to these two sets of equation, and by solving that, in almost all the 3D body, in 3D rigid body, you can go through these steps and solve the problem for the 3D problem.